Hey folks, in lesson 24 we're going to start applying the concept of angular momentum to our multiparticle systems. So just as a quick review, using linear momentum for multiparticle systems, we found some really interesting results. Most notably is that the total linear momentum, that we call P sub O, is equivalent to the momentum about the center of gravity, the center of mass of the system. And that allows us to do some interesting things with multiparticle systems. Most notably, that when we take the time derivative of the linear momentum of the center of mass, then that's equivalent to the sum of our external forces on the entire system. And so we get to ignore all of the internal forces in any of the interactions. And so, what we're able to do is, if we can calculate the center of mass of the system, which we call G, then we can treat this just as if we're applying F equals ma to just the center of mass, or to the entire system as a whole. So we get that the mass, the center of mass, the total mass of the system, multiplied times the acceleration of the center of mass with respect to O, as observed in the inertial reference frame, is equal to all those external forces. So now, as we develop our ideas of angular momentum of a system of particles, take note of the similarities when we're looking at the total angular momentum with total linear momentum, and how that works in terms of the center of gravity, or center of mass. And so today we're just going to set up what total angular momentum is. We're going to apply it to a couple problems, and then next time we're going to start pulling in more about how the center of mass interacts with this. So first, let's define total angular momentum. So we're going to start by looking at angular momentum for a single particle, and so we've just written out these equations because all we're doing is we're taking what we've done for a single particle, and we've applied the notation that we're using now when we're dealing with multiple particles. So essentially saying that we need to now put an index, which we're going to call I. So it will be point I, angular momentum of point I with respect to O, which is an inertially fixed point, is equal to this R cross mv. And as we've written it now, we're just pulling our m out because it's a constant as well. So you've seen this before. Just put an index notation on this so we can then add up all our particles later. And then, of course, Newton's second law in angular momentum form for a single particle is, if we add the index notation, it looks the same, where we have the moment of I with respect to point O, and so we have both internal forces and external forces. So we're now introducing this separation of external forces on the system and then internal forces. So this will be between the particles. And so these are defined as R cross F external and then R cross F internal. And then we can simply add all these up. We have our index notation, and so we add it up for a total of n particles. So from 1 to n, we add this up for every single particle to get H sub O, which is the angular momentum, the total angular momentum as observed in an inertial reference frame. So now that we've defined our total angular momentum, to make this useful for our dynamic systems, we need to take the time derivative of it. And so the time derivative of our total angular momentum, and then we'll just put our entire expression within this. When we take this time derivative, let's pull our summation out. As you know from previous lessons, we can really do about what we like with these summation signs, moving them through in the calculus. And so when we pull our summation out, we're going to use the chain rule. So we'll get the mass of point I, and then the time derivative of our position vector is going to be our velocity vector. So v of I with respect to O, as observed in the inertial reference frame. And this will be crossed with v of I with respect to O in the inertial reference frame. And then continue with the chain rule, we have the mass of point I, position vector, then cross with now the time derivative in the inertial reference frame of our velocity vector. All right, so really quickly or really easily we can see that v cross v, or velocity cross with itself, is equal to 0. And then, in looking at the right-hand expression, let's just make this a little bit more like things that we've seen before. And let's switch this term here, where we can take out our m, r, and then cross, and then just replace that with r of I with respect to O, our position vector cross with mi. So we've just distributed our mass in here. And so the reason why it just makes us look at this term here, where we have our mass times our time derivative of our velocity, which is ma, which we should recognize as the sum of the forces on the system. And so we write this as Fi on this particle so this is Fi on the particle due to external forces, plus the sum of all the forces, and we'll say J is equal to 1 to n, of all the interactions, so Fi comma J. So now our expression for the time derivative of the total angular momentum looks like this, where we have the summation from I of 1 to n of r I with respect to O cross with the force on each particle due to external forces as well as all of our internal forces. So J is 1 to n of Fi comma J. Now, in the book, they rewrite this as the summation of two different terms, and the first term being r of I with respect to O cross with the external forces, and then separate out the internal forces in this manner. So you get a 1/2, and then both summations, so it's I from 1 to n and J from 1 to n. And this is r of I with respect to J. So that now this is the position vector between the particles crossed with the force between those particles, I comma J. Now we're not going to spend time deriving how this came about, but if you follow along in the book you can see how they split these up. But the important part here is now, instead of the position vector, which is the moment arm, r of I with respect to O, we now have this in terms of r of I with respect to J. So it's the position vector between the particles crossed with the force that's being applied by the particles. Now, recall back when we were working with total linear momentum, we were able to simply add up all these internal forces, and if we did this for every single particle, then they all canceled. And so we just canceled out that term. Here it's not quite that easy, and we have to introduce an assumption. And this assumption does hold for most of our situations as engineers, and it's certainly going to hold for all the problems that we work in this class. And this assumption is an internal moment assumption. And with the internal moment assumption, the internal moment being this term here, r I cross j crossed with f of I, Fi of the force on I by j rather, we're saying that this term, 1/2 summation of I 1 to n summation of j 1 to n of r I cross j, r of I with respect to j cross with the force on I by particle j is equal to 0. So this is stating that the moment caused by any internal forces about particle I, which is this expression, by particle j is equal to 0. And so in all of our problems that we're going to deal with, this is a pretty easy assumption to make, because the internal forces of our situation at least is acting along this position vector ij. And so if that's the case, the cross product has to be 0. And the reason why we can't just state this outright and say that because we've got Newton's third law, every force has an equal and opposite force, and then it's along the direction, is because in energized fields or magnetic fields, this just simply may not be true. And so remember, dynamics doesn't only apply to single particles, and rigid bodies is really kind of where we're going with this, but it also applies to particles moving through fields, and they interact with each other in interesting ways. And so, with this assumption that r cross f of all of our internal moments is 0, and this will be the truth in our situations, we now have a working expression in which we say the time derivative of the total angular momentum is equal to r cross f, so this is for all particles, and this is the moment simply due to external forces. So time derivative of the total angular momentum as observed in the inertial reference frame is equal to this total moment due only by external forces. Now, as a word of warning, don't get lured in to saying the time derivative as observed in the inertial reference frame of our total angular momentum is equivalent to the time derivative of g with respect to O. All right, we haven't made this assertion, and we can't say that this is equal to the moment about g due to external forces or anything like that. This type of analogy was true, or we proved that it was true in linear momentum, but this is not true in angular momentum. Now we're going to use the center of gravity or the center of mass to get some really interesting results, but right now don't be tempted to just say total angular momentum is equal to angular momentum about the center of mass. So let's apply this to a problem. Now recall that what we could do by having angular momentum of a particle and knowing this expression is that we could take the time derivative of that, set that equal to the moment, and then be able to efficiently develop equations of motion for a single particle. Well, now that we have our idea, we have this concept of total angular momentum is equal to the total moment, or time derivative of total angular momentum is equal to the total moment due to external forces, we can apply that to systems like this, in which we have multiple masses that are involved in the motion. The advantages are that we only have to calculate down to our velocity. We don't our kinematics to our velocity. We don't have to calculate all the way to our acceleration. And then also, if we're not concerned about the internal reaction forces, so the forces between P and Q, between O and Q, and between O and P, then we don't have to solve for those and put the entire problem together. So in fact, we have the tools from last chapter to be able to solve this, but it is pretty cumbersome when we have to go through all those constraint forces. So let's solve for the equation of motion of this pendulum that has these two masses. This is an equilateral triangle, so all the legs are length L, and then we have gravity, of course, which will allow this to move. So let's start by applying two reference frames. Our first reference frame is our inertial reference frame, and so we have this origin at point O, E1, E2, and E3. E1 we're defining as along gravity, E3 being out of the plane of motion, and then E2 being E3 crossed with E1. Then apply a reference frame that's fixed to this object that's moving, and so for this we have a theta in between our vectors E1 and ER. And so our basis vectors, our origin is still at O, ER, E theta, and EZ. ER we're defining as along the vector OC. So C, being a point that I'm making up, that's halfway in between point P and Q. And so that means that whenever theta is equal to 0, that our object here is flat. And ER is the same as E1 when theta is equal to 0. And then EZ being along the direction of E3, so it is also pointing out of the plane, and then E theta equal to EZ crossed with ER. The relationship between these two reference frames is given by this transformation table, which looks as we've seen before many times, and then we have the angular velocity of B, reference frame B as observed by reference frame I, as theta dot in the EZ direction. So let's start making our calculations. we're finding the time derivative, as observed in the inertial reference frame, of the total angular momentum is equal to the total moment due only to external forces. So we first need to calculate, let's work on this left-hand side. So let's find out what our angular momentum is. We'll take the time derivative of this, and then we'll set up the moment and equate those two to get our equation of motion. To calculate the angular momentum, we need to develop expressions for the velocity of both of our masses. So we need to get the good position vectors for those. And if we orient this along this direction, so we have an ER direction and we have an E theta direction as defined earlier with those basis vectors, and that's how we'll define our position. This is an equilateral triangle, so all of our legs are length L. And so this equilateral triangle, we can express this as just a 30, 60, 90 triangle. And so that means this dimension is going to be 1/2 L, and then the ER dimension, this vertical dimension, is square root of 3 over 2 L. And so with this we can write the position vector RP with respect to O as the square root of 3 over 2L in the ER direction minus 1/2 L in the E theta direction. To get the velocity of P with respect to O as observed in the inertial reference frame, we're going to take the time derivative of this. So we have the constant square root of 3 over 2 L, and then it's the time derivative of E sub r, and then minus 1/2 L times the time derivative in the inertial reference frame of E sub theta. And we know that the time derivative of a unit vector, so the time derivative of E sub r, is equal to omega b observed in I crossed with E sub r, which gives us theta dot in the EZ direction crossed with E sub r. So Z cross r is E theta, so we get theta dot E theta. And then the time derivative E theta is equal to omega b observed in I crossed with E theta. So that's equal to theta dot EZ crossed with E theta. And so it's theta dot, and EZ crossed with E theta is minus E sub r. So our velocity of P with respect to O, as observed in the inertial reference frame, is the square root of 3 over 2 L theta dot in the E sub theta direction plus 1/2 L theta dot in the E sub r direction. So these two expressions, our position vector and our velocity vector, are ready to plug into our expression for the angular momentum. And we'll do the same thing for point Q. And so it's R of Q with respect to O is equal to the square root of 3 over 2 L in the E sub r direction. And then this time we're moving in the positive. We have a vector in the positive E theta direction. And so this is plus 1/2 L E theta direction. And then the velocity of Q with respect to O, as observed in an inertial reference frame, is the square root of 3 over 2 L E sub theta. Oops, forgot theta dot. Minus 1/2 L theta dot in the E sub r direction. And now we have two more of our vectors that we'll use to find our total angular momentum. So our total angular momentum is equal to, for each particle, R of P with respect to O crossed with MP multiplied times v, p with respect to O, as observed in the inertial reference frame, plus the angular momentum of the second particle, rq with respect to O, crossed with mq, v of q with respect to O, as observed in the inertial reference frame. And so when we substitute our full expressions that have our coordinates into our form for our total angular momentum, we get r cross mv for particle p, and then r cross mv for particle q. So let's take those cross products. And so we get mp, and then let's do the r direction. R cross r is 0, and r cross theta. We write out the expression, so we get square root of 3 over 2 L, magnitude multiplied times square root of 3 over 2 L theta dot, and r cross theta is in the EZ direction. And then we have our mass again, and we're going to take our theta term and cross it with r. So it's a negative L over 2 is the scalar on the theta term, and then L over 2 is the scalar on, or theta dot, L over 2 theta dot is the scalar in the ER term. And so this is E theta crossed with ER, which gives us negative EZ direction. And so let's move on to our mass Q. And so for that we have the mass Q. We're going to take our ER term, cross it with our E theta term, because ER crossed with ER is 0. And so it's the square root of 3 over 2 L multiplied times the scalar from our E theta term and our velocity, which is the square root of 3 over 2 L theta dot. And r cross theta is EZ, positive EZ. And then we'll take our theta term and our position, cross it with our r term in the velocity. And so this is, we need to have our mq, and then it's positive L over 2. And then from our ER term, it's negative L over 2 times theta dot. And then once again it's E theta crossed with ER, which gives us negative EZ. So put a negative sign in front here, EZ. And then when we collect our terms, we get MP, and this is 3/4 L squared theta dot plus 1/4 L squared theta dot in the EZ direction, and this is plus MQ, and it's 3/4 L squared theta dot plus 1/4 L squared theta dot. And then our entire expression for our total angular momentum is equal to MP plus MQ multiplied times L squared theta dot, and that's in the EZ direction. So we'll take the time derivative of this to finish out our left-hand side. And so this is the time derivative as observed in the inertial reference frame of MP plus MQ, all multiplied by L squared theta dot in the EZ direction. And this gives us MP plus MQ, all multiplied times L squared, so all that's a constant. L doesn't change, the masses don't change. And then the time derivative of theta dot is theta double dot, and that's also in the EZ direction. So our left-hand side is finished, and now let's work on the right-hand side. For the right-hand side, we have the moment, it's the total moment due to external forces. And so to get the total moment due to external forces, we need a free body diagram. Our free body diagram of this system looks like this, where we have on particle P, we have the mass of P times gravity in the E1 direction. We're going to have the mass of Q times gravity, and this is also in the E1 direction because, recall we had E1 was pointing down, and then we also have a constraint force that we'll call N in the E1 direction. And so this is the point O, there's point P, and there's point Q. Now the only forces on this free body diagram that create a moment about point O are the force due to gravity on point P and the force due to gravity on point Q, or on mass P and mass Q. So we write this out as R of P with respect to O crossed with MP G in the E1 direction, and then plus R of Q with respect to O crossed with MQ G in the E1 direction. Let's put in our position vectors. And the cross products, and so we'll get R of P with respect to O cross with that force on P, and R of Q with respect to O cross with the force due to gravity on point Q. And you can see that we have cross products that are in mixed bases. We have our ER, E theta, and then we also have an E1. So if we transform our E1 vectors into ER, E theta, we get from our transformation table that E1 is equal to cosine theta ER minus sine theta E theta. And then after doing the algebra, we get that our total moment due to external forces is equal to negative square root of 3 over 2 L G sine theta of MP plus MQ plus 1/2 L G cosine theta of MP minus MQ. And this entire moment is in the EZ direction. So now that we have the entire right-hand side, we set that equal to the left-hand side, and we get MP plus MQ multiplied times L squared theta double dot in the EZ direction is equal to negative square root of 3 over 2 L sine theta G sine theta multiplied times MP plus MG, and then plus 1/2 L G cosine theta multiplied times MP minus MQ. And all this is in the EZ direction. So then when we solve for theta double dot to get our equation of motion, we get negative square root of 3 over 2 G over L sine theta plus an additional term, so 1/2 G over L, and then it's the ratio of MP minus MQ divided by MP plus MQ, all multiplied times cosine theta. So let's take a look at this equation of motion and make some sense of it. So the first thing you should notice is that we've got a term here that we recognize, which is negative G over L sine theta, which is our simple pendulum that has a length of square root of 3 over 2. So it's a scaled length based on the fact that this is a triangle. And so the second term that we have is a term that accounts for the differences in the mass. And the reason why you can tell that is because if MP and MQ are equivalent to each other, then this term goes to 0. The entire term does. And so we're only left with this scaled version of a simple pendulum. And so what we see here is that when we do have a difference in mass, that it's applying an acceleration that is equivalent to MP minus MQ over MP plus MQ 1/2. g over L that's out of phase by pi over 2. So this is a cosine term versus a sine term. And so it's in the opposite direction. This is a positive acceleration. This is a negative acceleration. And so it's an acceleration that's out of phase by pi over 2. And so what happens is when the masses are not equivalent to each other, or if they are equivalent to each other, let's start with that. If the masses are equivalent to each other, then if we give it a position response, so we've got some theta naught that we start with, then just like a simple pendulum, it's going to oscillate between the same angle perpetually. But if the masses aren't equivalent with each other, then what we have is, and let's say where MQ is greater than MP, then we can start it at the same position, theta naught, but then it's going to oscillate beyond theta naught on the other side, the negative theta naught on the other side. And so we're going to get an asymmetric oscillation in the pendulum, whereas it's symmetric if the masses are equivalent with each other. So that's how to interpret this equation of motion, and I encourage you to just plug this into ODE 45 in MATLAB, give it some different initial conditions, and you can see how this two-mass pendulum with similar masses, do that first, and then say pull it back to 45 degrees and let it go, and then do the same thing with pendulums that don't have equivalent masses, and see how the position changes over time. So using our total angular momentum, taking the time derivative, setting that equal to the moment about that inertially fixed point, O, due to only external forces, we can get pretty quickly this equation of motion. Now you could also do this by calculating F equals ma for either particle. You then have to account for the constraint forces between P and Q, the constraint forces between O and Q, and also between P and O, and then solve simultaneous equations. You can get the same answer, but it really is a lot more work. You also need to calculate the acceleration, which can be sometimes cumbersome. The advantage of doing F equals ma is that you can get those constraint forces easily, but also if you don't need those constraint forces, using this angular momentum approach can save you some time. So let's discuss just for a moment about the conservation of total angular momentum. And so once again we have parallels with total linear momentum from Chapter 6. We said in Chapter 6 that when we're looking at our total linear momentum, and when this is conserved, so the time derivative of our total linear momentum is equal to 0, then all the external forces on the system, the sum of all the external forces that act on the system, is equal to 0. So with our angular momentum, the parallel here is that when the time derivative of our angular momentum is observed in the inertial reference frame is equal to 0, then the moments, the sum of the moments on the system are equal to 0 as well. And so recall for a moment that we have this assumption here that this is also when all the internal moments are equal to 0. And just like when we were looking at the conservation of angular momentum for a single particle, this doesn't mean that there are no external forces on the system. We can still have external forces on the system. One of the key examples that we have, one of the most useful examples that we had for a force that applied to a particle was a central force, where angular momentum is conserved, but we still had that central force that was there. So just because there are no moments that are on the system, it doesn't mean that there are no forces on the system. So let's use our conservation of angular momentum in the problem that we've already done before and see how we can take this concept and make it work for us in an efficient manner. So here we've got this problem where we had the sticky impact with a simple pendulum. And we solved this using the total linear momentum. And what we were looking for was we wanted to find the velocity of the joint particle PQ. We've got Q that's approaching P. They collide with each other. They stick to each other. It's a fully plastic collision or a fully inelastic collision. They stick to each other. We want to know what the velocity is right after, immediately after the collision. So using total linear momentum, we had to carefully separate what the interactions were in the EX direction and the EY direction, and then we had to account for the internal forces which canceled out between each other, and then we also had to account for the effect of gravity. And so we couldn't just say that the linear momentum is conserved in this system. What we did find was that linear momentum was conserved in the EX direction, but not in the EY direction. And then with the constraint force in the pendulum, in this rigid pendulum, that applied the impulse which removed the velocity in the EY direction. And so what we found when we solved this is that our velocity was, so x dot qp, or pq, at time 2 was equal to mq over mp plus mq multiplied times x dot q at time 1. And so this is where, so this is our speed. This was in the EX direction. So the EX direction. And so this was where, this is the horizontal speed of Q just before it impacts P, just before we have the collision. And then this is our speed of the particle in the EX direction right after that. And so what we'll see now is that conservation of total angular momentum during the collision is going to allow us to solve this same problem very quickly. So during the collision, and let's draw our diagram. During the collision, we have a free body diagram that looks like this. And so on this we have particle Q, we have particle P. The only forces that we have are negative mg in the EY direction, and this is mass of P, and then we have on this also mass of Q in the EY direction, so the negative EY direction. And so if this is hanging from the pendulum, then the moment O due to external forces is equal to R of PQ with respect to O crossed with these two forces. So this is negative MQ G minus MPG, and this is in the EY direction. And so because this vector, this position vector R of P with respect of R of PQ with respect to O is also in the negative EY direction, this cross product goes to 0, and so we see that there is no total moment. So the right hand side of our equation of our time derivative of the angular momentum is equal to 0. So total angular momentum is conserved. And it's conserved only during the collision, because we're only looking at a small time that goes from time 1 to time 2 in which we have this orientation. Now after this collision, we know it's going to start on a circular path, and when that occurs, then the total angular momentum is not 0. And so we're solving for the velocity of that joint particle at time 2. And because total angular momentum is conserved, we say that total angular momentum at time 1 is equal to the total angular momentum at time 2, and that's all during the collision. So at time 1, point P is at rest. This is just before the collision. So if P is at rest, that means the only thing that's contributing to the angular momentum is the velocity of Q, the velocity and the mass of Q. So total angular momentum at time 1 is equal to R of Q with respect to O at time 1 crossed with the mass of Q multiplied times the velocity of Q with respect to O at time 1. And so let's solve this expression. Total angular momentum at time 1 is equal to negative L in the EY direction crossed with MQ, and then the velocity using Cartesian coordinates is x dot q in the ex direction plus y dot q in the ey direction. These are both for time 1. And then when we take our cross product, we get L, the mass of q, multiplied times x dot q at time 1 in the ez direction. Now to find the angular momentum, total angular momentum at time 2, our masses are now stuck together and they have the same velocity, and that's the velocity we're solving for. So we say it's r of this combined mass, rpq, with respect to O, at time 2, crossed with the combined mass, mass of p, plus the mass of q, multiplied times the velocity of pq with respect to O at time 2. And so this total angular momentum at time 2 is equal to, we get the same thing, negative L in the ey direction. So that's the same position vector, because during the impulse it hasn't changed position, it's only changed velocity, or it's changed momentum because it's changed both velocity, and now we have two masses. So this is crossed with the combined mass mp plus mq multiplied times x dot of pq, our combined mass, at t2, and this is in the ex direction. Let's take our cross product. And we see here that this is L of mp plus mq, so this is all our scalars, then x dot pq at time t, 2, and it's ey cross ex. Hope we need to have our negative scalar there. And then because it's ey crossed with ex, then we get a negative sign, so negative ez. So we get rid of our negative, and then this is in the ez direction as well. And so we set these two expressions equal to each other. So the total angular momentum at time 2 is equivalent to the total angular momentum at time 1, and we get L mp plus mq, so this is at time 2, x dot pq at time 2, this is in the ez direction, is equal to L mq x dot of q at time 1, also in the ez direction. And when we solve for xpq, or x dot pq at time 2, we get the same expression that we had before, which is mq, the ratio mq divided by the total mass mp plus mq, multiplied times x dot q at time 1. And so with this problem you can see that we came up with the same solution, but by recognizing that during the impulse, so from time 1 to time 2, the angular momentum is conserved. Okay, it's not conserved beforehand, it's not conserved afterward, but angular momentum is conserved during the impulse, and taking advantage of that, we could simply come up with these relatively simple expressions for our total angular momentum at both those times, set them equal to each other, and then solve for the scalar that we're interested in. So you can start to see some of the advantages of using angular momentum over linear momentum when you can. And so we're going to take this. Next time we're going to separate this into, we're going to use the center of mass to our advantage, pull this into the system, and then you start separating what's called angular momentum separation to develop an even more useful tool for solving these dynamics problems. All right, that does it, and I'll see you in class.